Assalamu alaikum. Bismillahirrahmanirrahim. I welcome you to the 25th lecture for the series of lectures on advanced computer architecture. Today, after a brief review of what we have discussed so far about the computer architecture, we will start our discussion onto what is outside the processor. In our earlier discussions, we first of all discussed how we can measure the performance of a processing system. Here we talked about different designs of the processor, its data path, and its control sections. We discussed the design of single cycle, multiple cycle, and pipeline architecture. We further analyzed the performance of a pipeline architecture in detail for instruction level parallelism. Then we discussed some hardware and software-based techniques to expose instruction level parallelism and to enhance the performance of a processor. However, we noticed that the overall performance of a processor can influence the overall performance of a computing system. But we cannot say that it is the only parameter or it is the only component whose performance can improve the overall performance of the system. Rather, the performance of a computer is very much influenced by what is external to the processing system. Talking about the performance of a computer without considering the performance of input-output systems is just like discussing the road performance of a car having a very powerful engine but without having any wheels. You can well imagine what will be the performance of such a car with very high power engine. So therefore, today we will focus our discussion for what is outside the processor and how the outside systems, they influence the overall performance of the processor as well as the overall computing system. However, whatever is outside the processor is always referred to as the input-output system. It is just like whatever is outside from the human brain that is regarded as input-output system, such as our hands, our eyes, our mouth, and so on. Similarly, for a computing system, the input-output system includes the most important component, memory system, and then the buses which are used to interconnect the input-output systems with the processor, and some control systems which are used to control the overall interfacing of the external systems with the processing system. So today, first we will discuss the memory system, which are usually designed in order to enhance the overall performance of a computing system. The design goal of a memory system for high-performance computers is to present the user with a much more memory as is available, such that a particular bit or a word is immediately available to the processor. However, from your earlier studies of digital systems and the basic organization of a computing system. You know that the fast memories are expensive, whereas the cheap memories are slow. Therefore, while designing a memory system, we have to develop a memory hierarchy which should be organized into several levels such that the memory is available with the cost which should be as low as the cheapest memory available and the speed as fast as the fastest memory available with the present technology. This block diagram shows you how a memory hierarchy system is developed. Here you can see that the memory system can be organized by using different types of memory blocks at different levels. These levels of memory system are organized with hierarchical arrangement of different types of memory modules, and these memory modules, they range from the fastest to the slowest memory. Besides variations in speed, you can see that these boxes also vary in size, and this shows that the smallest box is inside the processor and it represents the fastest memory but smallest in size, and the largest memory block is shown as farthest away from the processor, and it shows that huge memory can be made available by using some external devices. What makes this kind of arrangement work is one of the most important design principle, and this design principle is referred to as the principle of locality. That is, where each type of module is located in the memory system, whether it is inside the processor, whether it is close to the processor, or it is farthest away from the processor. Moreover, we can design the memory system by taking the advantages of the principle of locality. We provide to the user an average access speed that is very close to the speed that is offered by the fastest technology, and the cost that is very close to the cost offered by the cheapest technology. Here, from this point of view, we will discuss different types of storage devices. This is basically a review of what you already have studied at your undergraduate level. You know this thing that the semiconductor memories such as registers, static random access memories, and dynamic random access memories are fastest in access speed, but they are very, very expensive devices. Therefore, they are used in small size and are placed either inside the processor or very close to the processor. While the secondary storages, such as the disk or the tape, they offer huge storage at a lowest cost per bit. Therefore, they are placed farthest away from the processor. Now let us have a look onto the levels of memory hierarchy. Here, note that the access time units of the memory modules change by a factor of 10 from picoseconds to milliseconds, and the size units change by a factor of 1000, say from bytes to kilobytes. Furthermore, different levels of memory hierarchy, the information transfer between two levels is controlled by hardware means as well as by software means. The information transfer from register to cache and cache to register is controlled by the program as well as by the compiler at the compile time, whereas the information transfer between cache and the main memory is performed under the control of a hardware unit known as the cache controller. And the information transfer between the main memory and the secondary storage is controlled by the operating system as well as some built-in hardware. And finally, the information transfer between different types of storage devices, such as between the disk and the tape, is under the control of the user or the operator. Now, this diagram basically shows different levels of design hierarchy for the memory system. Here you can see that the topmost level is referred to as level 0, and it shows the level where the registers are placed. That is, the smallest memory units placed inside the microprocessor. The next two levels, which are shown as L1 and L2, are the two levels of a fastest possible memory with relatively higher in size, and this type of memory is known as the cache. The cache means hidden from the user. So basically this memory is kept hidden from the programmer, and its data transfer from the register to the cache or from the cache to the main memory and vice versa is controlled by a built-in hardware-based cache controller. Whereas the next level is the level of the main memory, which is usually implemented by using dynamic random access type of memories. We will be talking about this type of memories in a few moments. And the next higher level of the memory is referred to as the local secondary storage. The local secondary storage is one which is very close to the processing system, that is usually inside the body of the computer, and this type of storage is available in the form of floppy disk or hard disk, or nowadays the compact disk, that is the CD-ROM devices, etc. Whereas the next higher level is the remote secondary storage devices, and these remote secondary storage devices are in fact the distributed file systems such as the web servers, etc. Here you can note that the levels of hierarchy usually subset one another, that is, all data in one level is found in one level below. That is, the data which is, say, available at level 1 cache is also available at level 2 cache. And the data which is available in level 2 cache is also available in the main memory, and so on. Now, before having discussion onto the memory hierarchy, we will review the classification of storage systems based on different attributes and their design features. Based on different attributes, the memories can be classified as the semiconductor, magnetic, or optical memories. This is when we are considering the material of implementation of the memory. Whereas, based on the accessing technique, a memory can be classified as the random access, the sequential access, or the hybrid access. Whereas, based on what is the storing and retrieval properties of the memory can be classified as a read-only memory, read-mostly memory, and read-write memory. You have already studied the designs of these type of memories at your undergraduate level. Therefore, here we will simply review what are different types of memories and how they are designed and they are used in the hierarchical system of memories. For this purpose, we will first of all talk about the random access memory. The key feature of a random access memory are that a random access memory, which is in short referred to as a RAM, it is packed in a chip and its basic storage unit is known as a cell. This is usually 1 bit for one cell, and multiple RAM chips can be combined together to make a memory. The random access memories, as the word random indicates that it is a memory where any cell of the memory can be accessed randomly in same amount of time, whether it is located at the first location of the memory or it is located at the bottom of the memory. The random access memories can be implemented as the static RAM or the dynamic RAM when they are implemented using semiconductor materials. So here I would like to make one thing clear, that the word RAM should not be confused with ROM. ROM can be a random access and it can be a sequential access. But ROM can be distinguished from the read-only and read-mostly memories. As the word ROM indicates that it is the read-only, that is, this memory does not have writing capabilities for the programmer. It is programmed only during the manufacturing time. It is just like the program stored in the memory in a human head, with the help of which a newly born baby knows that how he can cry or how one can move his hands or legs. So whether this memory has been implemented by using sequential access techniques or random access techniques, it does not matter. Now let us look into the design of a static RAM cell. Here, each cell stores a bit of information in a circuit made of 6 transistors. This circuit retains a bit value indefinitely as long as it is powered up. Moreover, it is relatively insensitive to the disturbances such as electrical noise, and it is faster and more expensive as compared to dynamic random access memory. Let us have a look into this circuit and see how it works. Here you can see that the circuit consists of 2 back-to-back inverters that serve as a flip-flop. Here is an extended view of this cell where you can see that how the 6 transistors are connected in this circuit. In order to write a value into this cell, one needs to drive from both sides. For example, if you want to write a 1, you will drive the bit line to 1, while at the same time you have to drive the bit bar line to 0. Once the bit lines are driven to their desired values, you will turn on these 2 transistors by setting the word line to high, so the values on the bit line will be written into the cell. Here, please remember that these are very tiny transistors, so we cannot rely on them to drive these long bit lines effectively during read. Also, the pull-down devices are usually much stronger than the pull-up devices, so the first thing we need to do on read is to charge these 2 bit lines to a high value. Once these bit lines are charged to high, we will turn on these 2 transistors, so one of these inverters, in this example the lower one, will start pulling one of the bit line low, while the other bit line will remain at high. Now let us see how these basic cells are organized to design a big RAM circuit. For this purpose, let us have a look onto the design for a 16 by 4, which is 64-bit RAM. This means that it is consisting of 16 words, and each word in this case is of 4 bits. Here you can see that in this picture the 15 word and 14 bit, they are arranged in an array form. The word lines are connected horizontally to the address decoder, while the bit lines are connected vertically to the sense amplifiers and write drivers. Here, let us see what do you think that which particular line will be longer, whether it will be a word line or it will be bit line. The answer to this question is that the bit lines will be much longer than the word line. The reason for this is that a typical SRAM will always have thousands, if not millions of words, that is the vertical lines, and usually be less than tens of bits in length. Therefore, the bit lines are longer than the word lines. Here you can notice that this is a bad situation, because if we have a large load on the word lines, that is, there is a large capacitance, then we can always build a bigger address decoder to drive them. But for the bit lines, we still have to rely on the tiny transistors of the static RAM cell. That's why we need to pre-charge them to a high and use sense amplifiers to detect the difference. Furthermore, read enables is not needed here, because if write enable is not asserted, then the read is taken by default. That is, we do not need read enable line. Furthermore, the internal logic will detect an address change and it pre-charge the bit lines. Once the bit lines are pre-charged, the values of the new address will appear on the D out pin, that is the data output pin. With this much discussion about the static random access memory cell and the memory design, let us have a brief review of what is a dynamic RAM. This diagram shows the basic cell of a dynamic random access memory. Here you can see that each cell stores a bit with a capacitor and a single transistor. However, as the information is stored in a capacitor and practically the capacitor may get discharged with the time, therefore the value once stored in this capacitor must be refreshed after regular interval of times, which may range from tens to hundreds of milliseconds. However, a random access memory using single capacitor to store the information, it is very sensitive to the disturbances or say the noise, and also it is slower as compared to the static RAM, but at the same time it is also cheaper as compared to the static RAM. Therefore, the dynamic RAM cell is usually used as the basic unit in the design of the main memory system. Let us have a look onto this one transistor cell and see how read and write operations are performed. The write operation is very simple. We just drive the bit line and select the row by turning on this pass transistor. Whereas for read, we will need to pre-charge this bit line to high and then turn on the pass transistor. This will basically cause a small voltage change on the bit line, and very sensitive amplifier is therefore needed to measure this small voltage change with respect to the reference line. Once again, the value we stored will be destroyed by reading operation, so an automatic write-back circuit is to be included so that the memory read operation is not a destructive operation. Once we are familiar with the design of a single bit static cell, let us see how we can combine these cells to design a dynamic random access memory unit. In this diagram, you can see that we have got 16 words, and each word is of 8 bits. So we can say that this is a D by W RAM, where D is equal to the number of cells, which is equal to 16, and each cell is of 8 bits. These 16 cells have been organized here in 4 rows and 4 columns. Now, at each position, there is one cell of 8 bits in size, and we call this cell a supercell. Each supercell can be identified by its location in terms of the row number and the column number. For example, here you can see a supercell marked as supercell 2,1 means it is a cell of 8 bits corresponding to its location at row number 2 and column number 1. Let us see how different steps are being performed in order to read a cell from this dynamic RAM. The first step is that we can apply the row access strobe, that is RAS, select signal to row 2. And following this, the row 2 is copied from the DRAM array to the row buffer, as you can see from here. Then the next step is that the column access strobe, that is CAS, is applied, which in this example selects column 1. Therefore, now we are in a position to copy the supercell 2,1 from the buffer to the data line and eventually to the processor. Now let us see that how more than one memory modules can be interconnected to make a big memory module of the desired size. For this, let us suppose that we have got 8 modules and each module is of 8 megabyte. That means each cell is a supercell of 8 bits and it is organized in the form of row column structure having 8 megabyte of memory in each module. These 8 megabyte modules can be connected as shown over here in this diagram by applying a module select signal, which is usually the upper address part of the memory address line, which select a particular block or a particular module within this bigger 64 megabyte memory cell. So with this much discussion about the dynamic RAM, let us talk about some further extension in the design of the dynamic random access memory. The enhanced dynamic random access memories are built around the conventional dynamic RAM core which we have just discussed. In the normal dynamic RAM, we can only read and write m bits at a time, because only one row and one column is selected at a time by applying the row address and the column address. In other words, we can say that for each bit of memory access, we have to provide a row address and followed by a column address. So this shows that it is a very time-consuming process. We can overcome this problem in a fast address mode random access memory, as shown here, by placing a register of size n bit by m bit so that we can save an entire row internally whenever we access a row. We can improve the performance of this memory by redesigning it using the concept of fast page mode dynamic random access memory. Here, what we can do is we can put an internal register of size n by m, so whenever we access a row, the whole data is being transferred into this register. After that, we only need to provide the column address and assert the column address signal for other m bits at the same row. So this way we can make use of only one row address select followed by 4 or n number of column address selects instead of a row address and a column address repeatedly, as in the case of standard dynamic RAM. The other type of enhanced mode dynamic memories are known as the extended data out dynamic RAM, or EDO DRAM. This design is one where the enhanced fast page mode dynamic RAM is used with closely spaced column address select lines. The other type of extended DRAMs are known as the synchronous DRAMs or SDRAMs. Such RAMs are driven with rising clock edge instead of asynchronous control signal. The other types of enhanced dynamic RAMs are double data rate synchronous DRAM. It is one where the enhancement mode of static dynamic RAM is used with both the clock edges and the control signal. And the video RAM is one where, like the fast page mode DRAM, but output is produced by shifting the row buffer here. The dual ported allows concurrent read and write operations in this particular case. So with this much discussion onto the dynamic RAM, let us see what are the other types of memories which are being used in the memory system. The other type of memories are referred to as the non-volatile memories. These are the memories which do not lose information even if the power is off. These memories are, in fact, classified as the read-only memories, having capabilities either do not allow to change any information once this information has been stored. And in the read-only memories, the information is stored at the manufacturing time, as I mentioned earlier. The other types of read-only memories are the programmable read-only memories. The programmable read-only memories can be programmed once in a laboratory. However, once programmed, then the information cannot be changed. Whereas another type of read-mostly memory exists, which is also non-volatile, but this type of memory is known as the erasable programmable read-only memory, or EEPROM. These type of memories, their information once programmed can be removed by using ultraviolet light source. By using this ultraviolet light source, we can erase the previous information and we can restore the information into it. The other type of memory in this class is known as electrically erasable programmable read-only memory. That is, we can erase the information electrically instead of using ultraviolet light onto it. The other types are the flash memory. As we discussed earlier, for the design of the memory hierarchy system, the other type of memories which are used to store bulk of data are known as the secondary storage devices. The most commonly used secondary storage device is known as a disk. Let us have a look onto how a disk works and what is the geometry of a disk. Here you can see that a disk consists of platers, and each plater has got two surfaces. Each surface consists of concentric rings known as the tracks, and each track is divided into number of sections. Each section is known as a sector. The sectors on a track are separated by gaps, as you can see from here. Then the number of platers are arranged onto a spindle at the central position, where they have got two surfaces for each plater. Here in this example, you can see there are 3 platers, so there are 6 surfaces starting from surface 0 up to surface 5. The capacity of a disk is defined as the maximum number of bits that can be stored onto the disk, and it is usually in the range of gigabytes for a disk. Presently, the disk storage up to gigabytes in the range of hundreds of gigabytes are available. However, the capacity is determined by different factors. For example, it is determined by the recording density, that is, the number of bits that can be squeezed into 1-inch segment of a track. And the areal density is defined as the product of recording and track density. Now let us see that how we measure the access time for a disk. The access time for a disk is defined with the help of different types of times. For example, the average access time to some target is approximately defined as the sum of the average seek time plus the average rotation time and the transfer time. Here the seek time is defined as the time to position the head over cylinder containing the sector. The rotation latency is defined as the time waiting for first bit of the target sector to pass under the read-write head, and the transfer time is defined as the time to read the bits in the target sector. So with this much discussion about different types of times, we can calculate the overall average access time by adding up all these 3 times, and it usually comes in milliseconds. With this much discussion about what are different types of memory modules which are being used in the development of a memory hierarchy, we can observe how the gap between the dynamic RAM, disk, and the CPU speed is changing. This can be observed from this graph, where you can see that the reduction in the time starting from 1980 up to 2000 in the speed of the disk, or in the seek time of the disk, is very small as compared to the decrease in the seek time for the dynamic RAM and the static RAM shown over here. Now, today I will stop here with this much discussion about the different memory systems. Next time we will see how we can combine together different types of memory modules, and we can design a complete memory hierarchy system. Till then, Allah Hafiz.